So I'll start the first presentation with this 4D experiment and simulation and data challenge. First of all, I would like to remind some of you who don't know the BIGMECA chair, what are the objectives. Right now we are about midterm, so it's a good moment to take a break, present our results, and ask for feedback of the community.
Jabra speak 510.
So I'll give a few words of introduction, and then I will show you some experiments and simulation, and tell a few words about international collaboration we have ongoing in the BIGMECA. So if you're here in this room or online, you know that materials are the core of tomorrow's challenges, and this statement has been probably true for centuries, but it's even more true today. We've to move from fossil fuels to more renewable energy, we need better materials with improved properties. We need better processes to make those materials, and we need lighter structures to reduce fuel consumptions and improve energetic efficiency of our systems. So the BIGMECA initiatives build on top of the tremendous progress we have seen in both material characterization and material simulation in the last perhaps 10 years. We can do now new types of characterization. You will see this with tomography and so on. And you can do also tremendous simulations of material behavior that was not possible before. So we build on those strengths, and to dive into sort of a new paradigm, the digital twin. Whether you speak about a material specimen or an entire component, we can now characterize its life and simulate the life, including some of the service loading. This is a difficult task because you then face a data challenge, because both the characterization and the simulations are very, very costly. But we recognize that by merging experimental and simulation data, we can better identify the physical mechanism at work behind deformation and degradation. And we also can achieve fast prediction of the properties of the components. And you will see example of that in the talks today. So very briefly speaking, to face this data challenge, we decided to build a new data platform for the mechanics of material. And I will not get into the detail now because we have an entire presentation by Aldo this morning. And you will see how this will help in the future to achieve those objectives. So very quickly, the BIGMECA Research Chair, funded by Safran and École des Mines, chaired by me and David here, is running until 2024. It has a PhD program, it has a postdoc program, we have master students from the DMS program all over the course of the research initiative. We have educational actions toward our students to let them to those topics. And also international collaboration I will touch upon later in the talk. We studied primarily two really research thrusts. The automated 4D mechanical testing and machine learning, I will talk about now, and also model and data reduction for ultra-fast simulation. And you will see example of that in the presentation of Axel this morning, and other presentation by David and Fabien this afternoon. Right, so now I've explained a little bit what was the idea behind BIGMECA. We'll now first introduce this 4D and experiments and simulation. And I want to remind you, or tell you that at Centre des Matériaux, we have built quite an expertise on building in situ thermomechanical stress rigs to work at the synchrotron or in tomographic lab sources. This has been quite successful, I would say, and this is the point where I can't put all of them in one slide. We have many different stages. So in Clément's presentation, for instance, you will see example of study with this bulky rig, but we have many different test rigs for different thermal and mechanical conditions. And one of the hot topics now is to move to more complex geometries with plane strain specimens that were difficult to do with the tomographic setup. And we are modifying the static tension rig in collaboration with XNovotech to do this for the testing in the lab DCT setup. And maybe we can ask, if you have questions about this, I can answer, but I won't cover this in the talk. Just a brief recap of what we do. We take the stress rig to the synchrotron and you put your material specimen inside, and you're able to essentially do a three-dimensional characterization during a mechanical test. That's what we call 4D testing. And it's come to a point where you can do the test without stopping. You can do your imaging without stopping the test. So you end up with a stack of 3D images after the test that you have to process. And it's so it's quite a lot of data that we have to manage in the end. One of the modality I tend to work to push and to work and to develop, and that's one of at the heart of one of the research thrusts in BIGMECA, is the diffraction contrast tomography modality. I won't get into the detail here. Clément will explain this in the next talk. So essentially, you can think of it of a non-destructive 3D EBSD. So this is an example where we have mapped all the grains of a gauge length of a specimen, meaning that once you've done that, you can naturally build the digital twin of the specimen. If you do this, you might be able to use the map to conduct, for instance, simulation of the material behavior, and you'll see example of that this morning. Or you might want to do finite element simulation, perhaps to look at crack propagation or whatever. So we need to mesh the microstructure. So we've been doing that for a few years now, and I'm pleased to let you know that thanks to Frank Nguyen's work, we have that fully automatized, and this is part of the BIGMECA data platform. So it's a little bit of a teaser of Aldo presentation, but essentially once you've done that, you can mesh your specimen with one line of Python. But perhaps also because you have everything, because everything is well managed within the data platform, you have the local frame that is also taken care of. The grain IDs would be appropriate with their orientation, and with one more line of Python, you can create the input file for the ZSET simulation, mechanical simulation file.
Regarde également sur la 6336-5, je pense que tout le monde sait ça. Sur
one of you. So once you've your specimen meshed, probably if you study metals, you want to use a crystal plasticity model to try to predict the plastics activity inside the grains. So we won't getting too much into the details here. We use a classical finite strain model developed at San Matteo by Samuel with the multiplicative decomposition of the strain gradients that allow you to compute on one side the plasticity inside the grains based on the Schmidt law and the available slip systems. And also within this E-tensor, you access the lattice for the rotation of the crystal lattice, which is something we measure during our experiments, and which is something we want to compute and compare with our simulation, or with our experiments, sorry. So if you've used this model, you know that materials parameter calibration has always been an issue. So typically what you do is run some tension compression tests and then you would use some kind of mean homogenization scheme to identify the parameters. But this is sort of a little bit of a problem, because we now access local values with our experiments, and we optimize our parameter with respect to macroscopic testing. So just to let you know that this is still an issue. We want to use the local values to identify the parameters, This is a difficult problem. We are starting to look at in a different PhD thesis, the one of Daya, who will present this morning, but on his DMS work. And this is the PhD with David and Lionel Gelebert at CEA. Okay, so that was a bit of the tools we want to use to do these 4D experiments and the concomitant simulation. And we already understand that there is a big data challenge here because of the amount of data that is involved and the difficulty to manipulate it. And part of this will be answered in Aldo's talk. But I want to show you a brief example of such experiments. This is something I've been showing here before, so I will be very quick. If you have questions, you can ask in the chat. So this is an experiment it's a fatigue experiment. So we did, this is a titanium alloy. We did that some years ago at ESRF. So we did exactly what I showed you. So we DCT the sample first. So we have the entire gauge section with the grains. And then we grew the crack and did tomography every 1,000 cycles. So in the end, we end up with hundreds of tomographic scans that we need to segment to get the crack shape out of the volume. And then we need to register everything together so we know in which grain the crack is growing at which speed and so on. We did that rather manually at that time, and just another teaser of one of these presentations this morning is that now we have a deep learning pipeline to do the segmentation automatically, and this will help a lot to doing this kind of experiments. So if you're interested in doing 4D fatigue testing on small specimen, looking at crack growing in 3D grain networks, we have the tools to do this. So in the end, you end up with this image where the crack is growing inside the grain network, and you can see the crack slowing down and accelerating at some points, branching in some grains, and this is what we want to study. So we figured that to study this, we need to know the local stress field, the plasticity field of the crack tip. So we went to the digital twin side of things with our colleagues from Purdue University. And that was FFT simulations with Ricardo Lebenson code, where we input the grain network and the crack shape for every instance, and then we computed 100 fatigue cycles for each step of the crack growing, and then for each time snapshot, if you want, we have then the grain network, the crack shape, the stress, the plasticity you had of the crack tip. And then we can, because this is on the same grid, it goes into the same data set. And you sort of merge that together to build a huge experimental and simulation data set. Then we can use this data set, so we split it into different parts, and then we can use the training data to train a Bayesian network to learn how the crack propagate. So what will be the crack direction given the stress, the plasticity, the grain orientation, and so on, and also the crack speed. So we trained the network to learn that, and that was quite successful. We had a few papers on this. And we went even a bit further, where we even proposed a new closed form equation for the crack propagation direction in the grains. Okay, so that was one of the story about the fatigue cracking. You will see more this morning. And now I want to switch gear a little bit and show you a different technique, some really new results. So if you, right now I have been talking about, classical tomography and also the diffraction contrast modality, where you shine a specimen with a box beam. So you illuminate the specimen, the entire specimen at once, and you collect information on the entire gauge length. Now, if you want if you're looking to grain stuff, you may want to get more details for individual grains. And you can do this by using this topotomography technique that you can do at the ESRF on ID11. Essentially, you pick a grain from your DCT, and you align one of the scattering vector with the rotation axis. with this, you can achieve a full Bragg condition, so a diffraction condition for 360 degrees. And because we have the stress rig that allow to put on the specimen at the same time, you can look into the grain, you can peek into the grain in topography mode in situ. So essentially, you can see there is a real image rotating here. You rotate the specimen, and then you can still see the grain for a full 360 degree visibility. And because you're in topography mode, it means you're sensitive to crystal defects, such as dislocation and so on. So this is one of the techniques we've been using for the last couple of years, trying to see what we can do with this. So I'm showing you here a new study that we just published. This is on a titanium alloy in collaboration with my friend and colleagues at UC Santa Barbara. The specimen is here at ID11 and ASRF. So it's been installed on the goniometer that's allow you to do this alignment of the scattering vector for a given grain. That will be different for all the grains. So you have to rotate things around. And then you have the X-ray going through the sample, and then the topography is captured by this high resolution detector here. So I'll show you some results. So it's a bit a busy slide here, but you've here we do the DCT, right? So you have here the DCT reconstruction of more than 1,000 grains of this titanium specimen. And then from the DCT, we pick grains. So we were able to, so this specimen has been EBSD before. It received a high resolution DIC mapping. So we know exactly at the surface what are the slip system actives. We'll show a picture after. And then we do the topotomo. So we pick grains. So in the previous study, we did this already, but we studied only 3 grains. And it was kind of difficult to conclude on what are the transmission mechanisms, how plasticity proceeds. So here we automated the methods. So it's pretty much you program the diffractometer to scan all the grains given their orientation. And then we mapped 55 grains in 2 different neighborhoods. So because we have the DCT, we can pick grains and its neighbors. So we did this. And then what you see in the topograph is what you have on the top. So right, you see here a grain. Here I'm showing you one particular angle where you see those bands. And if you look at the crystallography and the geometry, you see that those bands are actually slip bands. So you can, from that, you can infer what is the slip system active in this grain. And we can do this in those many grains, and you end up with this these figures on the right where you have all the grains remain transparent and all the slip plane active has been popping up. And because we have so many grains, now we can study how plasticity transmits from one grain to the next. And that's what I'll show you now. And this is managed with the data, the BIGMECA data platform. So you have example here because, as I told you, we did EBSD and micro DIC on the surface. You see here on surface grain we have all those bands that are resolved very finely by the high resolution DIC. And with the topotomo, we decided to image both bulk grains because we can do it and because that's what we want to study, and also surface grain to compare with the DIC. So here are both 2 examples in the surface grain. You can see that it match very well the slip bands. There's only the very low intensity bands that we don't capture with the topotomo with the current state of the reconstruction. But if you look at this grain, for instance, you can see things you would expect. In this blue grain, the plasticity transmits to the red grain. And if you, from this 3D view, you almost see that the slip planes are compatible, or even the slip direction are compatible. You can calculate that with an M prime factor, which is one of the factors we use for assessing the compatibility of slip system across grain boundaries. And which approach is 1, it means that it's easy for the plasticity to transmit from one grain to the next. And in this case, it's 0.7, so it's quite high. And this is what you would expect. If you compute all the M prime factor for this red grain, you see that the slip system active is the one with the highest M prime factor. And by the way, this slip system is not the highest Schmidt factor, right? It's picked because it's transmission effect from one grain to the next. And you can see with those experiments, you can really inform mechanical models. And yeah, we have a different behavior on the bottom, but that's what I want to focus. So we have this comparison at the surface, which is nice. But then we wanted to study the difference between surface and bulk. And interestingly enough, in the bulk, it's different. So people have been studying this, right? This kind of results has been known for a few years using actuaries and Sunday IC. They've been doing the same kind of things, but people tend to generalize this to the entire volume. What we found in the bulk is that it's not so much like this. If you plot the distribution of the M prime factor in the surface and in the bulk, they're quite different. They are high at the surface and they tend to be lower in the bulk, which means that it's not so much, the plasticity is not so much driven by transmission in the bulk. We think that other factors such as triple junctions, small concentrations at the grain boundary can trigger plasticity, and not so much the transmission from one grain to the next. So if you're interested, we just published this, for it's under review, but you can have a look at the preprint. It's on archive. You can just download it and read more about this. So we're running out of time. So just a few words about international collaboration we have in BIGMECA. We have a collaboration with we do a lot of DCT at the synchrotron, but we have collaboration with people doing lab DCT because this technique is moving to the labs quite fast. Fortunately, we don't have such equipment in France. So we work with Stephen Hall at Lund University, and I think Clément will talk about this because he's just got back from Lund 2 days ago. Also, we have today we'll have the pleasure to have Samantha Daly giving a talk at the end of the seminar, and we're very happy to announce that she will be at Centre des Matériaux next year for a few months. She will be a PSL visiting fellow, doing some teaching that actually already started and some research collaboration with us. So we are very excited that to start this collaboration with the Daly's group in UC Santa Barbara. And Samantha will show her work today, but she's been doing a lot of work in the same kind of fashion that we present today. And the funding is through this program for a little bit of, well, 1/3 by the BIGMECA and 1/3 by the École des Mines. If you don't know and you're interested by this topic, save the dates. We will have the international workshop on the mechanics of polycrystal that has been postponed for 2 years now due to COVID, but it's finally scheduled at École des Mines in May, in the upcoming May, so May 23rd to 25th. We'll have a hybrid mode, but you're welcome to attend in real life, and it's sponsored by BIGMECA and MECAMAT. We have a list here of invited international speakers, and so we are quite excited to have this 2-day workshop that will actually be held on 3 days. So it starts Monday, and it's Monday at noon and ends on Wednesday at noon. Okay, so just a few takeaway message for this first talk. I think we can say that 4D imaging has become very an important tool to study the mechanics of structural materials. We build on experimental progress and simulation that when you couple them, and I've shown you, you sort of face a data tsunami. And for that, we are developing a data platform that help to manage all this data modality, and will also allow you to do a better analysis, statistical analysis, machine learning analysis in the future. Thank you. And now ready for questions.
Thank you, Henry. So it's time for questions. I don't see any question in the chat.
Well, maybe in the room.
In the room. Who want to start? Yes, Ida. Please use the microphone and maybe. Maybe yes. Perfect. Yes.
Usually, given the same size of defect in the bulk, right?
Yes. Voilà, ouais.
Usually, when you have the same kind of defects and size of defects in the bulk and the surface, you observe that fatigue cracks tend to initiate mainly on the surface, and this is usually attributed to surviving the defect, which is probably true in most cases because you have some experimental proof of that. But given what you saw, do you think that maybe that it would be say different plasticity so that could explain this? Maybe if you have some grades cooperating, then maybe plasticity would be the reason for that.
Okay, so I will repeat the question so people on Zoom can hear it. Ida asked the question that when looking at fatigue, we tend to see that cracks initiate mostly at the surface. And she asked if the plasticity results I shown could be another explanation, because usually the explanation is an environmental effect. So I haven't thought about this. Certainly now we sort of see that we have the free surface in plasticity plays a role. We have so we see different behavior in the bulk and the surface. It's not so sure right now how much that affects the amount of plasticity that you can see. Perhaps this is something we need to look at. We see a different mechanisms, but it doesn't mean that the amount of plasticity is different. And you just have to accommodate that amount of deformation because you're prescribing it. And the materials find a way to accommodate it. So I can't answer this question right now, but certainly this could be an effect on fatigue as well, because this is for monotonic testing, but it's probably true for cyclic testing as well. But again, it's a bit of a stretch to yeah.
Thank you.
Thank you. We have time for another question. Yes. Use the microphone and speak loudly.
Thank you.
Closer to me.
Generally speaking, one of the problems we're going to have with is massive experience. It's hard to store them in the long run. So I know there's a lot of presentation coming up about that evolution, but mostly for the application of analysis. When it comes to experiment itself, have you explored, and that's a bit further from mechanics, properly speaking, but have you explored avenues to help us store this data in an efficient yet robust way?
Right.
Because in the end, if you were to use that industrially, it's something we're going to have to keep in the future.
Right. So the question is, those experiments was for the experiment generate a lot of data, and it's probably not tractable to especially for industrial partners to store them and keep them for a long time. And if we want to build, well, I'm just a bit stretching the question. If we want to build data methods, we want to use the data libraries and so on. So what do we have a think about and work on some methods to do this efficiently? So I guess the answer is yes. We will show you some example to some extent. We show you some example in the data platform, which is actually meant for that, to manage more efficiently, to use better compression algorithms. So there's a lot of progress that can be made. The downside is that at the moment, speaking about those experiments, we don't really have access to the acquisition system. So we cannot plug into the acquisition system. So right now the data is generated in first, and then we sort of at the post-processing step, we sort of repack it in an efficient way for us to the analysis. So we sort of duplicate it, but we can. I guess it's still answer your question, because you can just take this data, which is better managed for home. And nowadays, all this facility now, they store the raw data for you for at least forever. Now is this is the politics now. It's for now it's stored forever. So but it's not usually in a usable form. So this is the brick the step we are building is, I think, is really important, because if not, we are just not going to use it to its full potential. I mean, the example I shown you might have been successful, but it took us maybe 6 years or something for one sample, one experiment. And we want to do those by the tens. We want to do perhaps 10 of those. So we have to rely on those better methods to do this in a more automated way. So there is a question from Benoit. Maximum resolution obtained with DCT. That totally depends on the specimen size. You can go down. So for us, we've sort of say 100 micron grain size. We want to use a 1 millimeter, millimetric sample size. So resolution is typically 1 micron, 1.2, 1.4, which give you sort of the resolution. But if you have a smaller sample, you can go down to 0.3 micron with DCT. And then there have been other techniques that have been developed that I didn't explain, but the nano focusing scanning through the diffraction basically gives you the same results with even more precision, with a 200 nanometer spatial resolution. And also you get strains. So there is a lot of potential for those techniques. But we sort of wanted to keep it to the, well, to do the digital twin. So if you really go to finer scale, then it's kind of hard to do also the digital twin. So our take is that we stick to the sort of micron size resolution or millimeter size specimen with micron resolution. And then if we want, we can zoom in into different grains with higher resolution techniques, such as the one I shown with the topotome.